So if I have a vector A, how do I turn vector A into a unit vector?
Strip it of its magnitude.
We strip it of its magnitude. And how do we do that? What? Not B, A. A, and then we strip it of its magnitude of A. Over the last 2 lessons, we've been playing with some of our vectors and our dot products and some of the principles. It's the wrong word. I can't think of it. The applications of the dot products and the special things about dot products. For example, if I have some constant times my dot product, what's that the same as? Can I use my distributive law on that? You had a question that was like 2 times vector A dot minus 5 times vector B, and you had to work out what that was, and that ended up being the same as, yeah, A dot B times minus 10. So if we had the minus 10 out, we can distribute this one out. So we can actually have, let's call it, what am I going to call it? MA dot NB, where M and N are factors. So we can actually put them out and pull them back together again. We had another one where we had a vector dot times by an addition. And again, what did that one end up being? We could distribute that one out as well. So A dot B plus A dot C. And the last one I want to draw our attention to is what happens if I times a vector by itself.
Length square.
Or sorry, not times, dot product. What do we end up with?
Length square.
Length squared if these were lengths, or just entirely length squared? Does it?
Length squared.
Length squared. Why does timesing a vector by itself end up with the magnitude of that vector squared? Because my cos 0 is 1. So my dot product ends up being A times cos 0. So we end up with our magnitude squared, which is a scalar quantity. So today we're going to talk about 2 different projections, but they're related. The first projection we're going to talk about is a scalar projection. And this carries on from our dot product. Now when we talk about a projection, we're really talking about, and the analogy you're going to hear everywhere, is about the shadow. So if my pen was a vector and I was shining a torch on my vector, the projection is the shadow that this pen makes with some other vector. Now at the moment there's no other vector underneath it, agreed? So it's not making much of a shadow. But if I had the vector as the desk, I would have a shadow of this vector. So if we draw that up, here's my vector, and I have some other vector that I am, projecting vector A onto. Now when I project vector A onto, it's the same as if I dropped 2 perpendiculars down from my vector. Remember, I've got my torch shining down, and my projection is this vector, this length here. Getting my terminology mixed up. And if it's just a length, then it's going to be a scalar projection. Do you agree? Now, this length here is the same as this length here. Do you agree? Yep. And if we knew this angle here, can anyone, let me say that this is vector A, I'll put it more obviously there. Can anyone tell me what would this length be? A cos theta? What A? Just A? Vector A? So you're saying this?
Yeah.
Magnitude of 2.
Why magnitude of A and not vector A?
Because the vector has a direction, you need a length for that.
So the vector has a direction, and it's actually just the length that we're dealing with. This is straight trig. Do you agree? Yep. Now, this would work if we had two vectors in this direction and they were actually tail to tail. We would get the same sort of projection. And of course, that's for a what sort of angle?
Right.
Acute, yes. If we had, if we had an obtuse angle between my two vectors, I would still get the projection, but my projection is down in an opposite direction. And we don't need to worry about that too much because our sign of cos will actually tell us it's in the opposite direction. Do we agree? Let's call this projection, which isn't that, let's call it C. So we're going to say that our projection is equal to the magnitude of vector A times cos theta. Now if C was a vector, because we tend to turn everything into vectors at the moment, we would be able to make the same statement by just talking about the length of that vector. And we will go to vector projection in a second. We okay so far? Now, this is the basis of projections. It is something you know. But we do take this and turn it into something that we deal with more with vectors in terms of using our dot product. So, if we were to rearrange this, we would get that cos theta is the magnitude of C divided by the magnitude of A. Agreed? But from the dot product, what is cos theta already? We already have a cos theta in terms of the dot product. What is it? A dot B over? Excellent. So we can rearrange that to get cos theta times our magnitudes, which is our second version. And if we now have this in here, of course you don't need to write all the steps. C over A. Can you see that our magnitude of A actually becomes a little bit irrelevant? We end up with the magnitude of B times the magnitude of C. So we get yet another definition for our dot product. And we can rearrange this if we wanted to come back to what our magnitude of C is. We okay with that so far? Okay. Let's do an example and then we'll go on to do our vector scalars. So in our example, I have a vector A, which is 5i minus j. And I have a magnitude, a vector B, which is, and I always fail to read them, 3 plus 4. Now, if I want the projection of A onto B. Now, because I'm in an I and a J direction, those two directions are nice for us, but we have the vector A being shone onto the vector B, which isn't necessarily a horizontal. In fact, 3, 4 is going to look like a rise of 3 and a run of 4. This is going to be my vector B. Agreed? My vector A is 5 minus 1, and it doesn't need to be connected, but we want to know how much of it is shining onto our vector B. So to do this projection of A onto B, we need to work through all of these, and your A's and your B's might be slightly different, but not really. We've done A onto B. So if we want to work out what the projection of A onto B is, which formula do you think we're going to use?
Wait. Yeah, that one.
This one?
Yeah.
This one will give us the answer. So let's see if we can project through. The projection of A onto B is equal to A dot B over the magnitude of B. Notice, what is B over the magnitude of B? It's the unit vector B. Do you agree? So we can say unit vector B, but we need to do it anyway. What's our A dot B? Well, that's 5i minus j dot 3i plus 4j divided by, what's the magnitude of B? Sorry. Square root of, I know you're all going 5. Square root of 3 squared plus 4 squared, which is 5. I'm going to pull it out the front. There's my 1/5. What's my dot product here? 5 times 3, which is 15 minus 4, which is 11, so 11/5. So 11/5 of my vector A, which is a rise of -1, so something like this, somewhere, 11/5 of it hit this projection of B, or 11/5 of B are covered by it, is probably a better description. Hey, I'm judging by the noise that we have an answer. No? Yes? What's your answer? No? Answers? Thank you. It's a pretty ugly answer, so feel free that if you get something that's not nice, it's okay. I'm looking at you two and going, do you have an answer? Excellent. 11 over root 26, or 11 root 26 over 26, if you want to rationalise your denominator. Okay, I can work through that one, but for now, what I wanted you to note, because we want to get on to scalar vector, to vector projection, is I want you to note that these are not equal. Now let's think about that for a second. Angad had a bit of a laugh at my drawing because I said 11/5 of B was in the shadow of A. So 11/5 of B is in the shadow of A. That should mean that A covers up B 2 and a little bit times. So A is sitting there like this and shining down this shadow on it. Agreed? What is 11 over root 26 as a number? What is it? Someone type it in.
2.16.
2.16. So you should have more confidence then. So again, the shadow of B onto A is also more than 1. They're casting more shadow than the actual initial vector. Okay? And we get that. We know shadows.